Yeah.
Our topic paper is due on the 17th, right?
What?
Our topic paper
Okay, so we're gonna discuss that. What day is 17th?
is Thursday.
Thursday. That will be the earliest it's due.
Okay. Make sure I saw it right.
My class yesterday convinced me to move it to Friday. But we'll talk why that is. I assume you guys won't argue against that. I'll give you the option though if you really want.
Is our final exam over everything?
Yes, it is.
You can't ask about my topic, because I had an original topic I wanted to use, but I wanted to change it.
Okay.
So does it have to be chemistry based or can it be science based?
Chemistry based.
So what about the warrior gene? Is that not chemistry based?
What is that?
It's basically a gene that's found in the brain that says you're going to kill. It's basically saying that either it's always pumping in your brain or you're going to kill somebody. It's what's called a warrior gene.
Okay. So as long as you include some chemistry of it, which would not be hard to do in that situation, you'll be fine. Obviously, it's going to lean in heavily towards the biological aspects, but if you're talking about the makeup of the brain, the chemicals of the brain, the say dopamine or whatever the outcome of that gene is, that would all be chemistry as well. So that should be fine. Yes.
Where you said print sources, can those be like journal articles, or do they have to be like a physical book?
No, journal articles are perfectly fine.
Okay.
It doesn't have to be. It just has to be. You reminded me, so thank you. Has to be like printed somewhere, which is kind of, yeah. I know you're not physically holding them for the most part or things like that, but that's not a problem. That's not why I care about it. Someone stole my black marker. Maybe purple. It's probably enough of me whining. Okay, welcome back to class. Hopefully everyone is having a good week. The weather's gotten cold, so there's frost in the ground in my house yesterday. This was the first time I saw that, I think. I've got several announcements about the class in general and so forth. I made a list so I wouldn't forget. First and foremost, extra credit for the third exam. I'm going to announce that next class. I want to put some final touches on it, but it's going to have to do with what's called information literacy, basically like evaluating information that you see. I haven't quite come up with what I want to do about that, but I think it's really important, especially in the context of chemistry and society or science and society and so forth. Just yesterday, I actually thought of this like a week ago, but just yesterday, Google and Facebook both announced they have programs now to kind of downplay false news and things on the feeds that they've got, which kind of brings it to the forefront. In today's day and age, when I was a kid, there was a lot of value in knowing information, being able to recite information back and so forth. In today's day and age, that's not necessarily true because you can look it up so quickly. Everyone's got a phone. If I want to know how many people live in the United States, that's not something I have to remember. I just look it up. Okay? But of even more important in today's day and age then is being able to decide whether or not that is good information. So, this has been in the news a lot lately because of the election and so forth. I'm not necessarily thinking of it in terms of that, but evaluating sources of information is an important thing. Very beginning of the class, one of the very first slides, I talked about this a little bit. If you remember, we looked up the Smurfs on that one. I always look up whether or not Smurfs are real, and so forth. So that's what we'll do. I'll have that for you next time. It'll be the normal percent and so forth. I'm going to return the exams today to you. Overall, the class did fairly well, especially for this exam. This is a harder exam. The average was about a 75% for the course, which is right where it probably should be. The normal average for this exam is a little lower than that. It ends up being about 68, 69. So as a class, you guys did probably half a grade better than normal in the past. That doesn't mean everyone did as well as they wanted, obviously. So if you're one of the people who are upset about your score or are unhappy about it in any way, shape, or form, you can talk to me. We can see about going over it and so forth. The main thing about that is the final exam is comprehensive. So it's going to run from the very first day of lecture all the way to the end of lecture. And because of that, you'll see these types of problems again. The two problems at the end, going through and doing a naming and then shape and so forth, that will be on the final, as well as a math problem of some sort. Now in the final, it'll be a smaller percentage because there's a lot more information than what we just covered in the last exam, but you will see it again. So looking it over and correcting your mistakes is very useful at this point. Okay, so I'm going to return the exam at the end of class today. Don't let me forget to do that. They're sitting there, so hopefully I'll remember them and so forth. And then we can answer questions about them and so forth next time. Extra exam makes sense? Any questions there? Okay. Everyone seems really tired today. I'm not sure everyone wants to just stay bundled up in bed. This morning I woke up and I didn't want to get out. So I'm in the same boat, I think. My stupid dog. My dog calls me. Okay, next up, topic paper issues. So first and foremost, the due date. Originally the due date for the topic paper was today, but as I emailed you, I was going to extend that because of the exam last class period, so I didn't have a chance to remind everyone that the topic paper was due. So I extended it to Thursday, but then my class yesterday told me that by extending it one day, I put it on the same day as a clipping is due, and they didn't like that. So they convinced me to not have it due until Friday, the end of Friday. And that doesn't matter to me anyway, because I won't grade it before Friday. So it won't make any difference to me. So I guess with your guys' approval, we will have the due date for the topic paper Friday night at midnight instead of Thursday night. We don't have class on Friday to remind you or anything, but just remember. I guess that's what I'll say there.
Is there like a way
Yeah.
you want it set up, like on Blackboard?
Okay, so on Blackboard, if you go, actually I can call that up real quick. I got Blackboard open. If you go in here to the topic paper folder, right here is view assignment to submit it. So if you click on it, up pops this. Oops, sorry. And on yours, you're going to be able to see a submit. It's like a little arrow going up. It's like a box and then an arrow off to the side. You click on that and then attach your file to submit it. And that's the way you go about doing it. I ask that everyone submits a soft copy, basically an electronic copy, because that's what gets checked through the plagiarism checkers and things like that. Okay. So, yeah, good. At least one person's been able to submit it, I see. The other thing I was going to mention about that is if you do have problems submitting it through the turn it in here through this link. Give it a try and wait like an hour and give it a try again, just to see if you can do it. But if after your second try you can't do it, just email it to me. For some reason, certain students have problems getting them submitted through here, and we haven't been able to figure out why that is. So give it a good try, but if you can't do it in the first or second try, just send it to me directly. And then I'll upload it for you. I can bypass the system and upload it that way. So you can do that as well if you're having issues. The other thing about the topic paper I'll mention is formatting. Yesterday's class, you guys get the benefit of being in second class. Yesterday's class was asking about how to format references and so on. I don't care as long as you have references in some sort of format I can figure out. The reason for that is because all of us come from different backgrounds, different disciplines and so forth, and every discipline has a different way of formatting things. So because of that, I just want you to do whatever you normally do within your discipline. Chemistry has their own, but it's only for chemistry. It's even different than other sciences. So it doesn't make any sense for me to require you to do the chemistry type of formatting and so forth. So just format it however. If you don't know how to format it, MLA is a very common formatting method used throughout the disciplines. So you can just look up MLA and do it. Nowadays, you can actually go online to certain websites and they'll format it for you and so forth. I think it's maybe more effort to put all that in just to get a format out, but up to you. Yeah.
So in the assignment, you said something about footnotes.
Yes?
Is that the formatting or is that the little notes at the bottom of the page?
So if you're using footnotes for your references, then you can go ahead and do that. It's perfectly fine. Or you can put them at the end as endnotes. That doesn't make any difference at all.
Okay.
If chemistry uses footnotes, but other disciplines don't, or some other disciplines don't. So I don't know all the different formatting for all the different disciplines, obviously, so it doesn't really matter to me. As long as you've got like the name of the book or article, the author, and I guess maybe a date, I'll be fine with it.
Okay.
Yeah. So don't overthink the formatting. And if you got like a little 1 and then you put it as a footnote, that's fine. Or if you got a 1 and you put it at the end as that. Some disciplines will write like the author's name in the brackets for their reference and so forth, and that's fine too. Any of those types of things will be fine. The thing I do care about, I do check for, is the fact that you do have the 3 print sources. So, yeah, just make sure you have 3 of those. Any other questions about that? Okay, so that's the topic paper. Do not blow the topic paper off. It is a large portion of your score, and do not plagiarize your topic paper. I look for it, and I have in the past caught people numerous times. Yeah?
The print text, it can be journals too, correct?
Yes.
Okay.
Mhm. Yeah, it can be anything that is in print anywhere. And it's not really the best way to do this, but the reason I do that is because of what I was talking about earlier with information and judging information and deciding whether or not it's good information or not. Usually, historically, print has been checked against facts and so forth, and not just some random blog or something like that. That's why I said print sources, because it's easy to tell. But you don't have to hold it or anything like that. And journals are perfectly fine, everything like that. Yeah.
So would like science magazines be okay?
Yep.
Okay.
Yep. Yeah. The way I think of it, since I say print, anything that is on paper anywhere in the world at any time is good to go. And that's perfectly fine. So, I mean, yeah, it's not a perfect system by any means. Pamphlets, things like that would count as print, and I'd be fine with that. You're going to get the benefit of the doubt. So, and also, I'm not going to go looking for them necessarily. Other questions about the topic paper? Okay. So, as I said, the next clipping assignment is due next class. So let's not forget about that. This will be the final clipping assignment, I believe, for the course. It will be, today's Tuesday, so it'll be Thursday. So the beginning class Thursday. Yes.
When are you gonna put it on? It's not open up on.
Oh, it's not?
No.
It just has the
It
last
just has a
one.
clip and three.
Okay. I could even remember it. So there's assignments. Yeah, I'll put it up. Sorry. I don't know why I checked. I totally believed you. Okay. Okay, so yeah, I can put it up for us, and then we will be good with that. Anything else I'm forgetting?
Does that EC stand for extra credit up there?
It does.
I'm pretty sure I probably missed the opportunity because I came in late. Can you repeat it?
I'm going to announce it next class.
Oh,
That's all.
okay. Just
No problem. Yeah, next class we'll go over all of that. The final thing that I wanted to talk about a little bit here at the beginning of class is class itself. I have a handy dandy calendar. I keep track of things. And looking at this, we have counting today's class, we have 1, 2, 3, 4, 5 classes left. Okay, 5 lectures left. Or 5 lectures. Okay. The last week, on the Tuesday of the last week, which will be December 6th, that will be our last chapter exam. And that will cover everything from today until then. And then Thursday of that last week, we will spend reviewing for the final. So that day will be all review. In the past, I've had people ask if I'm going to take attendance or anything on that day. No, I'm not. It's just completely review for your own benefit and so forth for the final. And then the final will be the week after that. So we have 5 classes left in here, 5 lectures left for me to talk. We lose some time because of Thanksgiving, just getting in and out of Thanksgiving. We also lose some time for the last clipping assignment. So we really don't have that much more material left or time to cover material in the class. Because of that, what I want to do is I want to skip past the end of chapter 5, the types of reactions, combustion and single replacement, double replacement, and so forth, and move directly into chapter 6. Yeah.
So our next exam is our final exam?
No, your next exam will be December 6th. It will be the last chapter exam. Then the week after that will be the final, and it will cover everything.
So starting with this is what it's gonna be starting with?
Yes, if no one has a huge argument against this. You do? Okay. What would your argument like to be?
I just think it's gonna be very difficult for us to have the test on Tuesday for that and then have the
Oh.
cumulative final exam
Okay.
next week. 'cause
What else?
It's gonna be a lot to study on
What else would you like to do? What would be the alternative?
to put that,
Take on it.
to take the test that's gonna be for what we're covering now and on and put it into the final exam, just make it one big test.
Or you could just start with the combustion and the replacement, and that would just kind of add us a little time, and then it would kind of.
Well, see, if we do the combustion and stuff, you're gonna have more information.
Right, so we would probably rather have more information and just do it over like a chapter, than probably have way more information and do it over. Seems like-
No, I don't.
Like, rather than having a little bit at the end of chapter 5 and chapter 6,
Okay,
having that like as our end of year
okay,
test for like basically one chapter for an exam, rather
Okay.
than having an exam over 4 to 5 chapters.
well, the final exam is gonna be over the whole class.
Right.
Okay, and that's not really debatable.
Oh, well
But is that what you were saying? Like
I don't
having the
know.
final be over just this last section?
then, yeah, but I mean, if that's not debatable, then.
Yeah,
let's
no,
just
that's,
keep going.
okay, yeah. That's because,
Would you ever consider a take-home exam or
no. You would not like a take-home exam. I fell for that once. I was a student and my professor said, hey, do you want a take-home exam? And I said, yes. And now with the take-home exam, you have unlimited information. So I can literally write any question I want, and I failed it horribly. Everyone in the class failed it because of the amount of time that it took to do it and so forth. So, okay, so I guess the So I don't want to pretend like I'm just blowing off your suggestion here. The reason why, let me explain, the reason why we do the fourth exam over the chapter and then the final right away is the fact that by having it on the Tuesday, we can have an exam over the material and you can see where you stand in terms of it before going into the final. So you get it back on Thursday, and then you can have it to study for the final. If we didn't do that, going into the final, you wouldn't have any test over your understanding of the material until you get into the final. And then that section of the final would have to be probably a third of your final of new testing information. And I don't necessarily think that's fair, because all of a sudden now your final would be worth 30 to 40% of your score, and a third of that would be brand new. So I don't
So
like that.
what we're learning now is not gonna be on the final.
It will be on the final.
Okay.
So what we're learning now, you're gonna get tested on the Tuesday before the final.
And then it's
you-
gonna be on the final again.
And then it's gonna be on the
Okay.
final again.
Is the final exam, is that made up from stuff that we've already done, have been tested over? Okay.
Yeah. So when you're studying for the final, what I generally tell students is that the final is made up of between 90 and 95% of the stuff that are on the previous chapter exams. Because if I think it's important enough to be on the final, then it's important enough to be on the chapter exams, because I've got to thin it down every step of the way there. So it'll really be the most important things from the chapter exams going on to the final there. Now, there will be some that is overarching between chapters that doesn't fit right. Like, for example, nuclear chemistry, we're going to talk about today, has to do with the nucleus. So nuclear chemistry is on exam 4, but then the part about the nucleus is actually on exam 2. So those are kind of overarching between them. And that would be the 5 to 10% that doesn't come directly from them. They won't be the exact same questions, but like the formatting and things like that. The long questions of what is the name, is it ionic, covalent, is it polar, and so forth, that will be the same. I'll just change the elements. But the other ones will be on the same train of thought. Okay, so what I'm going to do then is move on to chapter 6 and start talking about nuclear chemistry. I don't think the reactions are super important, and I do think that nuclear chemistry is important. As a matter of fact, nuclear chemistry is the one thing I've promised to myself in teaching this class that we will talk about and go over every semester. Yeah?
Yeah, I'm sorry, one more question.
No, of course.
So, from chapter 6, from here on, it's going to be on the last chapter.
Yes.
All right.
Yep. So this is going to be the beginning of the information for the last chapter exam. So your notes or whatever, if you draw a line and so forth, so be it. The reason why I think this is so important is because this is a chemistry and society class. And in today's world, nuclear chemistry and nuclear sources and so forth are a very, very important part of everyday life. It's important in terms of your lives and what you actually do. It's important in politics. It's important in the economy. And all over the place. You can see examples of it. Just yesterday, I heard that a nuclear power plant, I think it was in Tennessee, was just sold to a private company that are going to make power from it and then ship the power all over the United States, basically. It was a TVA power plant that never got finished, and they bought it and they're planning on finishing it. It's supposed to cost a few $1 billion to finish it. So you can see what kind of investment's involved there. So, nuclear chemistry, I say it's everywhere around us. Can anyone think of an example of something that is related to nuclear chemistry? Yeah. With Iran? Yep. Mm-hmm. That I would fall into, actually, that has to do with the development of nuclear weapons. And this is a huge, huge issue in the world. We're not going to spend nearly the time that it deserves to discuss this in this class because we're not a politics class and you can spend multiple classes on just this issue. But world politics is very largely determined by whether or not a country has a nuclear weapon. Once they have a nuclear weapon, everything relation-wise with that country changes. At least in the past it has. Right now, two major countries we're worried about in the United States would be Iran. With the Iran deal, the new president-elect said he's going to throw that deal out. So we'll have to see whether that occurs and how that actually affects things. And then the other one is North Korea. North Korea supposedly has developed nuclear weapons in the last year or two. So we'll see whether or not that's going to change relationships with that country or not. Okay, so nuclear weapons. The other part of this that always goes hand in hand with nuclear weapons is nuclear power. So nuclear power plants. I just mentioned a minute ago, a new one is being built in the United States and coming online in the next decade. They take a long time to build and so forth. So these always go together because they are essentially the same. Okay, this is a really important point in understanding the world as we know it. Nuclear weapons and nuclear power are the same thing. The only difference is in a nuclear weapon, the energy is released all at once, and in nuclear power, the energy is slowly released. So they come from the same thing, they use the same materials for the most part. The main difference is nuclear weapons, the energy is released at once, power is slower. Can anyone else think of other things related to nuclear in our lives? Well, one very common one are smoke detectors. Smoke detectors use radiation sources, and what actually happens in those is the source is a beam of radiation, and the smoke stops that beam of radiation. And because the smoke stops that beam of radiation, the alarm will go off. That's how a smoke detector works. This is also why if you ever have the unfortunate experience of having a smoke detector outside of a bathroom or where you take a shower and stuff, the steam will do exactly the same thing as smoke. It blocks the beam of particles, and when it blocks it, it sets it off. I had a smoke detector in the house I rented right outside the bathroom, and almost every morning, the stupid thing would go off. So we just took the batteries out of it, which is not a good thing to do. I'm not very smart sometimes. Okay, so smoke detectors. The other ones are usually medical. So X-rays, CT scans, things like this. Pacemakers actually have a nuclear source inside of them because you can't just use a traditional battery with a pacemaker. Obviously, you can't just switch the battery out or recharge it. Something like that doesn't work. So they use little tiny bits of radioactive material to power pacemakers and so forth. There are other ones as well. Food we eat. Food we eat is radioactive. Not all foods, but many foods are. This is probably one of the most radioactive things you will come across in your life are bananas, believe it or not.
Why?
So the reason why that is because potassium is one of the more common forms of potassium is actually radioactive. And because bananas have such a high potassium content, they actually will give off radiation. You can use what's called a Geiger counter to measure radiation, and a good Geiger counter can actually measure the radiation coming off of like a bunch of bananas.
So what would that do to your body, like if you're
Nothing.
not okay?
Nothing.
You're good.
It's such a low level that our bodies have adapted. We are actually exposed to we're exposed to radiation all the time. Microwaves are. Now microwaves are generally enclosed, so that keeps the radiation in.
So
But
people say don't stand so close to the microwave. You might,
yep,
like, die or something.
that's exactly why.
Is that why pregnant women aren't supposed to stand close to microwaves?
Well, I wouldn't go with just women. It's not.
Why does it like,
But-
usually when you're pregnant, they say like when a microwave is going,
Yeah.
you stand next to it.
The reason for that is because radiation is particularly damaging to fast reproducing cells. So the faster a set of cells reproduce, the more dangerous radiation is for it. So when you're pregnant, the baby is literally a fast-growing bunch of cells. So they are particularly susceptible to radiation. So pregnant women need to be careful around radiation for that reason like that.
But I don't know what. So is it ultrascan?
Ultrasound is not radiation, it uses sound. You do get exposed to radiation, but again, it's a low enough level that it's not a big deal.
So is that also why radiation is used for cancer treatment?
That's exactly why radiation is used for cancer. Cancer, by definition, cancer is actually hundreds, if not thousands, of different diseases. Cancer is defined by the rapid, uncontrolled growth of cells. Okay? So because they are rapidly growing, cancer cells are particularly susceptible to radiation. And that's also why you get the side effects you get from radiation treatment. Hair loss, because the follicles of your hair follicles are rapidly growing cells, so they die off. Stomach lining is another one. That's why you see a lot of stomach problems with radiation and so forth. Fingernails are another one. So it all traces back to the fact that the more rapidly cells reproduce, the more dangerous radiation is formed. Now microwaves, in today's day and age, are perfectly safe as long as you're not circumventing the safety features. When I was in college, I circumvented my microwave safety features because the little latch broke and it wouldn't turn on because that's a safety feature. The door has to be closed. So I just jammed aluminum foil in there and it worked fine to make my popcorn. Not my proudest moment, but don't circumvent safety features. And that's actually the very first thing that I'm going to say about radiation is when we're talking about radiation and so forth, we are exposed to radiation all the time. Okay? Just by being in this room, we are exposed to higher amounts of radiation than you are sitting at home. Okay? The people around us are giving off radiation. It is a cement building, so that's giving off radiation. So that's going to increase our amounts. But if possible, just avoid it. Okay, so here's the symbol for radiation. It is basically the same symbol throughout the world. There are small differences and so forth. However, this is the general idea of the symbol. So if you see it and you don't need to be around it, then don't be. Okay? Kind of like when I was a kid, they used to teach us if you see a down power line, don't play with it. The same thing here. If you see the symbol and you don't have to be like hanging out next to it, don't. Okay? It's just for your own safety, avoid it. Don't circumvent the safety features of radioactive things like smoke detectors. There are safety features built into smoke detectors so that you aren't exposed to the radiation. That doesn't apply anymore if you take your smoke detector apart. Okay? If you want to look at the insides and touch the radioactive thing, you can do that. But it just doesn't make much sense. It's just a piece of metal, by the way. So there you go. So don't circumvent safety. Here in the United States, we take safety and things like that very, very seriously. So you have to go out of your way to get exposed to industrial sources of radiation and so forth. Other parts of the world are not necessarily this way. One of the big issues with radiation and safety is disposal of radioactive material and so forth, especially things from like doctor's offices and so forth. They may not get disposed of properly and stored safely. There are numerous stories of, say for example, dental materials that are used to make x-rays and radioactive sources used in dentistry, just going into landfills in different parts of the country and so forth, which is never good. Here in the United States, though, that generally doesn't happen. And then finally, don't be afraid of radiation. If you do have a reason to be exposed to it, then by all means go ahead and do so. If you've got a broken arm and you go into the doctor's office, don't tell them you don't want an x-ray because you're scared of radiation. Okay? You need the x-ray to help your arm heal and so forth, so therefore you'll use it. Again, in the United States, we are very, very conscious about safety and those types of things in terms of radiation. For example, if you ever get an x-ray, what does the doctor or nurse or the radiology tech do before they take the x-ray?
They put the little thing over
The
your
lead
body.
vest.
The lead vest. In the doctor's office, or in the dentist's office, they put the lead vest on too, which doesn't make much sense because the x-rays are like up in your mouth. But there you go. If you get a chest scan at a hospital or something like that, the doctors or nurse will generally leave the room or go behind leaded glass and so forth. And the reason for that is not because you're getting a high level of radiation, but they may do a couple hundred x-rays in a day. So even if it's a little bit of radiation, that adds up over time. So for you, it's not a big deal, but for them, they want to just make sure they're minimizing their exposure. So they'll go behind leaded glass, which is actually the same idea as a microwave. The front of the microwave is special glass so that the radiation doesn't get out. That's why you have to make sure the door closes. So, radiation, as I said, is always around us. We are being bombarded with radiation at all times. There's nothing we can do about it. Even if we were to enclose ourselves in aluminum foil or lead foil and so forth, our bodies would still be giving off radiation. So this is something that we are used to as people. We have evolved to deal with this. One of the best sources of protection of radiation actually is our skin. Our skin is amazingly good at stopping radiation and protecting us from it. So some natural sources, our own bodies. The sun is a large source. Radon. Radon is an element. It's number 86 on the periodic table. This is a radioactive element. It's formed through the decay of other materials in soils and so forth. It's a gas, but it's a heavy gas, so it collects at the lowest levels. So especially in this area is one of the areas to be concerned about this in the United States. Radon forms because of our geology, and it collects in our basements. So if you buy or sell a house here in northern Kentucky or in Cincinnati area, you'll have to get a radon test before you can sell your house. I had to get one when I sold my house last summer, just to make sure that there wasn't any radon buildup inside the house. My new house that I bought actually has a system to remove radon from it. So they must have had a radon buildup at some point, and the new system they put in, it's literally just a fan. It's a gas, so you just blow it from the lower levels outside, and then it leaves. So it's not difficult to get rid of, but you do have to know that it's there so you can do something about it. To know that it's there, you can get some simple tests. There's a 1 week type test where you just put a little material in your basement for a week, and then there's a 6-month version, which actually works better, and you can see how much radon's present. The 1 week I think is like $10, and the 6 month is like $20 if you get it from the US government. So from our natural sources of radiation, I would say over 50% of your radiation exposure comes from this. Your age group, for the most part, is probably higher than this. I would guess probably 85%, because you don't have a lot of medical applications generally. You're not getting x-rays or CAT scans, things like that, as a normal routine. So I would guess your percent from natural radiation is a lot higher. The man-made sources you may be exposed to are medical, dental, some safety things. Having smoke detectors in our house does expose us to a little bit of a higher level of radiation, but at the same time it protects us from fires and so forth, so it's a good trade-off there. Industrial, depending on what you do. I worked at a national lab, and we use super powerful x-rays and so forth, so I was exposed to higher levels of radiation because of that. It just kind of depends on what you do. The construction workers sometimes get higher levels of radiation because of the materials they work with. But man-made sources are generally a small percentage of the total exposure. One exception to this is smoking. Several of the chemicals or elements inside tobacco, and they actually collect in the tobacco plants, are radioactive. So when you smoke, you're taking that inside your body, so your skin can no longer protect you from it, and it can lead to higher levels of radiation there from just simply smoking. This is not nearly as dangerous as the other side effects of smoking. That's why we don't talk about it ever as a radiation source or danger due to radiation. But you do end up with higher radiation exposure from smoking. We used to do a survey in our nursing class where students would go and then they would add up. Actually, I've got it here. You can go through and add up your different radiation sources and then see a total for it. You could always tell who was a smoker in the class because their radiation levels were higher than everyone else. But just looking at this, your radiation level, you can go through this form. This is on the NRC website, nrc.gov. That's the Nuclear Regulatory Commission. It's the governing body in the United States that oversees radiation and so forth. So here, cosmic radiation is 26 millirems. That's what you just get from space. Okay, everyone does that. Depending on where you live, you add more to that from being closer to space or being further away from space, actually. So the higher you go, the more you would add in. Cincinnati, I looked up, is about 500 feet, so we're at the lowest level there. Then if you live in a stone, brick, or concrete building, you add some to it. Water and radon. You notice there that radon adds 200 counts, where the amount from space is 26, so 10 times less. So your general radon. That's why radon is such an important thing to keep track of. And then other sources. Nuclear weapons tests, you add 1 to it. Okay, so radon again was 200, so this is actually a very, very small amount. It's about equal to flying 1,000 miles in a plane. Okay, again, you're higher up in the air, so you're getting more exposure. So all of the radiation you're exposed to because of nuclear weapons tests over the years is equal to flying in a plane for 1,000 miles. Just to put them in perspective there. And then you can go through, and there's a bunch of other ones. Watching TV, add 1. I always found that kind of interesting. Here's our smoke detector, 0.008, and then medical and so forth. A lot of people worry about living next to a nuclear power plant because of the radiation. Historically, that's not the problem. So if you look, it actually adds less by an order of magnitude than watching television to your radiation exposure. The danger of living next to a nuclear power plant would be the, heaven forbid, accident never occurring of meltdown at the nuclear power plant. And that's the real concern there. You're actually exposed to more radiation by living next to a coal plant just because of the coal that's used than actually a nuclear power plant. Now, we'll talk about this later on, but a meltdown and accident in nuclear power plants are incredibly rare. Okay? There's basically been 3 of them in the history of nuclear power as you go through it. Now, they're horribly, horribly bad when they do occur, don't get me wrong, but they don't occur very often. Yeah.
Was there something that happened, I don't remember now, was it Chernobyl?
Chernobyl? Yep.
That happened in the, late 80s?
86. 30 years ago this year, actually, is why I know that. Chernobyl is by far the worst. And the reason why I would say that one's the worst is because when the meltdown occurred, it basically caused an explosion of the nuclear material, and the containment building failed. So it's supposed to all be contained within a building so that it doesn't get in the atmosphere. This building failed, and it put the radioactive material into the atmosphere. And you can actually measure Chernobyl's radioactive material anywhere in the world now because of air circulating and so forth. So the radioactive material that escaped there can actually be found anywhere on Earth at this point. The other two that occurred did not have failure of the containment. 3 Mile Island was the first one, and that was in the United States. And then the one in Japan a few years ago kept containment, even though they're still dealing with it. And I say kept containment in terms of air, some water got out with radioactive material.
One in Cincinnati for no.
I don't think there's one in Cincinnati, or I don't think there ever was. There was plans to convert the one just over in Indiana into a nuclear power plant, but that was put on hold and never actually committed. Yeah?
Wasn't that supposed to be a nuclear power plant at first because of the way the smokestack was built?
I think so. I think it was supposed to be, but I think public outcry of having it so close to Cincinnati at the time made them not end up having a nuclear power plant. Where I went to undergrad, Cedar Rapids, Iowa, there's a nuclear power plant right outside of town. It wasn't a big deal or anything. Most people didn't even know that. What?
What does it do again?
A nuclear power plant?
Yeah, like what's the purpose of it? I'm curious.
Just to create electricity.
Oh,
So a nuclear power plant creates electricity exactly like coal does. The only difference is a nuclear power plant is heated using nuclear energy, where coal, you burn the coal.
oh, okay.
So that's the primary difference there. And we'll talk about that a little bit later on as we go through it. Yeah, I'm not worried about that. So looking at radiation historically, a lot of the discovery of radiation actually dates back to the time of the cathode ray experiments. And one thing that was found there was that when you excite the cathodes and they hit a metal piece, X-rays are emitted out. And film work with the X-rays and different minerals and so forth showed discovery. The most famous scientist and one of the primary discoverers of radiation is Marie Curie, probably the most famous woman scientist on the planet ever, hands down. She ended up winning 2 Nobel Prizes for this, one in chemistry and one in physics for her work with it. It's a very interesting story if you like to read about people or see what people's lives are like. She is an interesting case there. Again, another one of these scientists that started out incredibly, incredibly poor and then rose to fame over time. But that being said, she did not have an easy life in any way, shape, or form. Not to mention the fact that she was a woman working almost completely with males at the time period, which didn't work out so well for her.
So what she didn't know was like blind and deaf? Or is that not her?
Not her. I won't go any more into it than that, I don't think. She is buried in the French, I forget what it's called. Anybody, where the French bury their most prized citizens? I can't remember the name of it right now. But anyway, she's buried there with the most historically important French people. Okay. Now, what is radioactivity? Radioactivity is simply the decay of a nucleus. So if we look at a nucleus, remember the nucleus is made up of protons and neutrons. This is the Pantheon. No, the Pantheon thing. Okay. You have your nucleus. And inside that nucleus, you have protons and neutrons. What radiation is this nucleus breaking apart into 2 pieces. The first piece is a large fragment. This is called a daughter particle. This primarily is what makes up nuclear waste. So it's kind of the byproduct of your radioactive process. And then a small particle, which is radiation, and this escapes. So you have your material, and your material is breaking apart, creating a new element, and part of your material is escaping to the surroundings around us. Yeah?
And what, is that heat in the circle?
Yeah, protons and neutrons.
Protons and neutrons.
Basically your nucleus. So these types of reactions actually don't have anything to do with the electrons. They have to do with the nucleus themselves. So here, for example, is a radioactive source. Okay. So this is a radioactive source, and it's actually a very small source. Pass them around. Okay, so if I pass this around for you to take a look at it, don't try and steal it. Okay? I actually, let me start passing. It's not dangerous in any way, shape, or form. You can take a look at it and so forth and see what it is. So inside that plastic disc, there's a little bit of radioactive material, and that radioactive material is decaying as we go along. So here's another one up here on the document cam.
Aren't those the same things we used in lab last week?
They are.
Okay.
Yep. So if you had 112 lab, you saw these last week. They're just the radioactive sources. Now, inside this disc, there's a little bit of polonium-210, and it's breaking apart. So right now, out the bottom of the disc, there is a stream of radioactive particles being shot out. So if I turn it on its side here, see if I can get it to stand, I can measure that stream of particles. Actually, probably not with this one. Let me switch sources here quick. I can measure that stream of particles using my Geiger counter. Okay. So this is a little handheld Geiger counter. You know Geiger counters because they always have a characteristic sound with them. And you always hear the sound in movies and so forth. The sound doesn't actually do anything. It's just an effect. Okay, that little beeping sound. Okay, that's our Geiger counter there. So what's happening in this case is I have my radioactive material here. It's breaking apart. It's shooting particles out. That's going into the Geiger counter. And then every one of those beeps you hear is actually a particle hitting the detector. So particle, if I scoot it up, you can see the light. Beeps.
So what's considered dangerous?
So considered dangerous would be something like, well, the average US dose is 600 millirems, so a chest x-ray is 10, so maybe 100 millirem. Now, that doesn't really mean a whole lot here. These would be on the scale of probably 10 to the minus 10 millirem, so tiny, tiny, tiny amounts. Now, granted, we are counting it, it's just on a different scale. So, yeah.
If you do get exposed to it, is it forever that you're going to have like symptoms or
No.
whatnot, or is it something that purges its way out of your system after a while?
Yeah, so it's an immediate effect, and once the source is taken away, it doesn't affect anymore. So if for whatever reason you do get an exposure, you may get like, well, an example would be similar to like a sunburn. you could get a sunburn in a certain area or something, and then once you took the radiation away, that would heal itself. Assuming that there's no specific mutations and things like that. It's not like in the comic books where the superheroes get mutation and they get superpowers. Okay? That's never happened. So you don't think of mutations that way. Mutations are usually just small changes in the cells. Okay, so we have this beam of particles here, and what that beam of particles is, it's a small portion of the nucleus breaking off and then traveling through space. And it's traveling down to the Geiger counter there. And that's what we call radiation. Okay, that's getting annoying. Okay, questions about that at all? Other questions? No? So as I said, oops, shocked you, sorry. As I said, these are little radioactive sources. These are so small that the government doesn't even keep track of them. But larger sources the government have on complete lockdown, like they know where they are all over the country at any given time. I think I'd probably get in trouble if someone tried to pocket one. A couple years ago, someone actually tried to take one. That's why I say that. Like I sent 2 out and I wouldn't notice not getting 2 back. But so be it.
What would somebody do with it? Just steal it for the sake of stealing?
I guess. I don't know what they would do with it. There's no value in it or anything like that. I worked at Oak Ridge once upon a time. Oak Ridge is one of the national labs that are very famous for nuclear programs. They are where the process of a nuclear weapon was developed. And when I worked there, someone tried to steal radioactive material, actually. Now that was a significant amount that you could actually make a dangerous weapon out of, but they didn't get very far. They got like 15 feet out the door. They have it set up so when you walk in, you've got to walk in a fence, and then you got to walk all the way down like a block long between 2 fences, turn, and then walk back down a block to get into the door. So you can't just like come out the door and run. You've got to like walk 2 blocks to be able to move like 5 feet away from the door for various reasons like this. That stuff is locked down like nobody's business. It's kind of scary sometimes, the security of those places. Okay, so what makes a radioactive element? Well, most elements have at least one radioactive isotope. And when we're talking about radiation, we have to talk about isotopes specifically, not simply elements. And the reason for this is because some elements will have isotopes that are radioactive, and then other isotopes which are not radioactive. So hydrogen, for example, has 3 isotopes. You have hydrogen 1, hydrogen 2, hydrogen 3. And most elements have multiple isotopes with them. You're not going to need to know them by any means, but just the fact that they exist is useful to you. Out of these 3, hydrogen 3 is radioactive. Okay, it's called tritium. This is the radioactive form of hydrogen. Most elements have at least one isotope that is radioactive. Now, it's really, really hard to tell what's what. I will never say to you, is isotope this radioactive or something? There's no real way for you to know that. But just so you're aware that different elements have different ones. There's a very famous one called carbon-14, which would be carbon with a mass of 14. This is used in radiological dating, so carbon dating. If you've ever heard of archaeologists carbon dating something, this is what they're actually looking for here. And we'll talk about how that's done a little bit later on when we understand half-lives. So carbon 14. Do you guys remember isotope labels and how to read them and so forth? Yes. No. So on your paper, see if you can figure out how many protons and how many neutrons carbon-14 has. So carbon with a mass of 14. How many protons and how many neutrons? Okay, everyone got their ideas? So carbon-14, the number of protons is equal to the atomic number. So carbon is always going to have 6 protons. And then the mass minus the number of protons is your number of neutrons. So it's going to have 8 neutrons. 6 protons, 8 neutrons. And this is important because when we're talking about nuclear reactions and keeping track of them, this is what we're keeping track of, the number of protons and the number of neutrons as we go through it. And we'll show you that in a little while with nuclear equations, but that's what you're keeping track of. Okay. Everyone okay with that? Now, as I said, it's really, really tough to know what is stable and what is not stable. So looking at this, all these red dots here are stable isotopes. Okay? You guys aren't expected to know this in any way, shape, or form. I just want to show it to you. But it curves up in a general trend for stability. And then any isotope that falls outside of this range tends to be radioactive. So if it falls in this magical ratio between protons and neutrons, it ends up being stable. If it's out of that, then it adjusts itself back into that line. So if it has too many protons, then it loses protons to fall back in range of this belt. That's what it's called. And that's really the best way we have to explain it. We don't understand the actual math behind it in terms of what that is. You can talk to real scientists and so forth and see why, and they won't be able to tell you the most basic levels. So background radiation, just to finish up, it's everywhere around us. We are developed or evolved as people so that we can protect ourselves from it. And the largest risk that you guys are going to run across for the most part is radon. So just making sure that you don't have large amounts of radon in your house is actually a very, very useful thing. I would put it up there with having a carbon monoxide detector. Okay. Carbon monoxide is an invisible gas. You have no idea. You can't interact with it. Radon's the same way. Radon doesn't have a smell. You can't see it. You can't feel it, anything like that. It's either just there or it's not there. And you need one of these little testers to figure it out. As I said, the testers are not expensive. If you want to get the tester, I would recommend going to the University of Kansas website. They run a national program. Well, they'll send you a tester in the mail, you set it up, and then you send it back, and it's relatively cheap. It's like $10 or something. I have 2 of them running in my house right now. As I said, I'm in a relatively new house. So I ran a week one and sent that off to get tested, and I'm in the middle of running a 6-month one as well. And I think the total was like $20 for them, so maybe $25. So it wasn't a big deal. It's relatively easy to do, and that way you know whether or not you've got large amounts. Cincinnati, it is a problem because of the fact we're in a valley, in the river valley and so forth, and the types of rocks we have around us. Okay. So how do we measure it? Well, there's a few different ways to measure radiation. The simplest way is just measuring it as counts per minute. And counts per minute is 1 particle of radiation escaping per minute. That's a count. A particle is a count. And in terms of this class, that's how we're going to be doing our problems and so forth. We're just going to do it as counts per minute. So decays per minute or radiation per minute, anything like that. is all going to be basically the same as counts per minute. This is not the scientific way to do it. The true measure of radiation is called a Curie, of course named after the scientist. And then the more common unit is called a millirem. Rem is actually a very large number, so you generally see things listed as thousandths of rems, which is what a millirem is as we go through it. Again, for this class, almost everything is going to be in counts per minute, not in millirem or things like that. I think even my Geiger counter has counts per minute on it. So it's fairly common to see that. And how do we measure it?
Can you go back one
Oh,
second?
of course.
Thank you.
Oh. Okay, how do we measure it? Well, there's a couple different ways to measure radiation. The easiest way, if you have it, is just a Geiger counter. And a Geiger counter, you'll see it in the movies all the time, and it has a little handheld paddle here. They hold the box in their hand, and then they have this handheld paddle, and they walk around, and they measure radiation. Usually in the movies when they're doing this, they're in big biosuits and so forth, which, by the way, would do nothing to protect you from radiation, unless they're lead-lined. And if you had a suit lead-lined, I'm not sure you could move around. So that's it. And there's always a characteristic sound to tell you that it's a Geiger counter and radiation is present. It's amazing how many movies use this exact same thing and model. In this building, we have one like that, and then we have like a dozen that are different designs. By no means are they all that same design. It's just what they choose to show in the movies because people know it. So that is the easiest way. The other way that is much, much more common is called a dosimeter. And a dosimeter measures a dose of radiation a person gets. So if you work with x-rays or you work at a national lab like I did or something like that, they're going to give you a little piece of film. And they put that film inside of a plastic container so no sunlight can get into it, but radiation can pass through the plastic. So over time, as you're exposed to radiation, that dosimeter will actually darken. And then once a month or once every couple months, they'll take the dosimeter and take the film out, look at it to see how much exposure, how much radiation exposure someone has. They're normally clipped like on name tags and stuff like that. So if you go to the hospital and talk to the doctors and nurses and so forth, you'll see like a little disc or something clipped on a name tag. That's usually a dosimeter. They take them really, really seriously though, because if all of a sudden you go from 0 exposures to high exposure, then they want to know where you're getting exposure from. And they take it really, really seriously. A friend of mine left his dosimeter without thinking in the back of his car, under the window. And because of that, it was exposed to the sun all day and the heat, and it darkened the film, and they kind of freaked out. So if you're ever wearing dosimeters and so forth, it's really important that you treat them well so that you can get good measurements from them. The other type of dosimeter I've seen are rings. They'll make rings of the same type of material, and that's for industrial people who work with their hands around radioactive materials so they can reach in and so forth and then see exactly how much their hands are being exposed. Their body may not be exposed, but their hands are because they're reaching inside of it. So that's how we go about measuring it. If you were in the lab last week and you did the nuclear experiment, you used a form of a Geiger counter, actually, in counting your counts and so forth. Okay. So that's where we're going to end today, because I want to hand back to exams and so forth. Any questions right now? Okay. So as usual, I'll hand back the exams. Once I hand them back, you're free to go, and then we will answer questions about them and so forth next time. Okay. All right, here we go. Troy. And again, let me give you my apology for messing up.
No problem.
Okay, Christian. I'm going to go with Sonnet. Bryce. Ariel.
Thank you.
Autumn. Jerry. Evan. Josh. Yeah. Amanda A. Amanda. Amber S. Andrew E. No problem. Stephen or Stephen Hall? Kylie M. Oh. Yeah, I guess it's Kylie. Okay. Dylan C. David G. Garrett A. Garrett. There you go. Okay. Zach. Gary. Ranish. Dakota. Destiny. Catherine.
Yeah, thank you.
Joe. Sorry about that.
No, that's not it.
Jacob. Oh wait, check that. Is that yours? The other Jacob. Otto.
Yeah, I got it.
Okay. Did you get yours back? Oh, that's right. Okay.
So I was just like,
Okay.
I haven't started.
Okay, does everyone have their exam back?
Yes.
Okay, great. Thank you all. Okay, great. Yeah. Okay. Oh, okay. Okay, yeah, so the chapter, or the exam 2, what was the exam 2? The exam 2 extra credit was, the Nobel Awards.
So what did you tell her? She said.
So, okay, so the Nobel Prize is given every year. And yep.
That's my thing. No, she had like, she said, she doesn't know if I get.
Yeah, that would be perfectly fine. Yep.
I'm watching, like, why?
Yep. 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 Perfect. Okay. Oh, what did I mess up?
I only counted 9 out of 23 wrong.
Oh,
We were at
okay.
13.
Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So this was a freebie.
Which one?
Number 10
Okay.
is a freebie, so it's actually out of 22.
Or 22.
So if you take 13 and 23, that adds up to 40 plus 1. The
Okay.
freebie is the 40.
Okay, so it's 134 out of 200?
200.
Okay.
Yep.
Okay. Thank you.
No problem. Keep up the good work.